The whole world, the whole market issue, people want markets, etc. So that's relevant to this as well. But everything's changing. So it's a sort of really awkward situation. Everything's changing. There's this chicken and egg problem, and there's also this incentivization problem. And incentives don't only necessarily mean market incentives. There might be grid codes. So it's a very multi-dimensional space, is the way I put it. Very complicated. So I think this is a very interesting topic. Okay, so Julian, we're going to ask Julian to talk first. And Julian, in fact, Daniel from SMA was mentioning the Pathfinder. So Julian, for your information, previous presentation by Daniel from SMA, he mentioned Pathfinder, so it's already been introduced. And then Tony from Australia will give his talk. And then I may say a few words about DS3, which is what John was going to talk about. And then we'll have Q&A. Okay? Okay, Julian. So I have to introduce you. So Julian Leslie is Chief Engineer at National Grid SO, and he's in charge of planning. And he's also heavily involved in the Global Power System Transformation Consortium and some others. Okay, Julian, over to you.
Great. Thanks for that. Hopefully you can hear me and see my presentation.
We can definitely hear you and we can definitely see it.
Brilliant. Thank you. Well, thanks for the introduction, Mark. It's a great pleasure to be here. I would have liked to have been there in person, but diaries and challenges of travel meant that hasn't happened. So I'm Julian Leslie, Head of Networks and Chief Engineer in the Electricity System Operator here in Great Britain. So I'm just going to talk about how we've sort of addressed the need for new services on the grid as we move through further decarbonisation, and how, as Mark said, how we've incentivised the market to innovate and to bring services and products forward to the market. So let me see how to. Okay, so I mean, nothing new on this slide. Everybody in the room, I'm sure, knows and understands this, but certainly in GB, we are rapidly sort of moving through this decarbonisation process. We are 66% lower carbon today than we were just 8 years ago, with only 3 coal-fired power plants left, which run less than 1% of the year in GB. So this is real for us. We've had our highest penetration of wind just the other week at just under 20 gigawatts of wind, and now it's on a demand of about 30 gigawatts at the time. So a huge shift over the last few years to where we are today. And that generation isn't where the coal-fired power plants were either. So it's moving around the country and is very far north of GB, up in Scotland, which is less densely populated. So then there's all the challenges of moving that generation around. So I guess, and all our new generation is pretty much asynchronous, so inverter-based connections, whether that be solar. We've got 12 gigawatts of solar, whether it's wind, with, as I say, 20 gigawatts of transmission-connected wind, and probably, we're not really sure, but 20 plus gigawatts of embedded inverter-based generation also on the DNO systems. So all of this is leading to a much more challenging scenario and situation which we need to manage in real time, both today, but obviously as we move to the future, very much more so. So we as the system operator, we have an ambition that in 2025 that we'll be able to operate a zero carbon grid system in GB. And the government announced just before Christmas, or maybe it wasn't earlier this year anyway, that we will have 100% zero carbon electricity system 100% of the time by 2035. So this is becoming really real for us. And as you know, 12 years between now and 2035 is not a long time in this industry. So really having to move at pace to make sure the systems are ready and we have a network that's fit for purpose. So the consequences of all of this and where we need these new services, we are seeing huge power flows across the system, which are only there for a few hours when it's windy and then they disappear, then they're back again. So how do you manage that? Is transmission investment, is that always the right answer when it's only used 50% of the time of the year, whatever it might be? So how do we manage that? And obviously the fewer synchronous generators on the bars, we have a reduction in inertia, short circuit in-feed, voltage control capability as well with the megavar range. So we, with the Pathfinders, are really out there in the market seeking solutions to ensure that the system is secure and it's at least cost to the consumer and facilitates this zero carbon generation. So what are Pathfinders then? It sounds like in the room you've heard about Pathfinders already this afternoon, which is great. And these are called Pathfinders because when we set off on the journey, probably what, 2 years ago, 2.5 years ago, we weren't sure how these were going to work. We weren't sure of the commercial arrangements we were going to have in place. We weren't sure of the regulatory structure in which these were going to participate. And we weren't sure of the technologies that were going to come forward either. So by calling them Pathfinders, here in GB, that gives us a bit of regulatory flexibility. It lets the industry know that actually this isn't going to be plain sailing. There will be questions along the way that we need to ask and address. So these were very much a trial to see what is the best way to approach getting these new system services onto the grid system. Because of that, every one that we do is very much learning from the previous one, and we change and adapt and improve. Such that now we've ran probably 6 or 7 Pathfinders across the various system services over the last couple of years. And now we're at the point where actually these are no longer Pathfinders. We need to find a new name for them and break them into business as usual as something that we do on a regular basis and update it on a regular basis. But very much our approach from the beginning was that we are not going to define the solution. We are going to be very clear with the system need, whether it's voltage control, short circuit infeed, inertia, thermal control on the system, and put the need out to the market and then say to the market, this is our need. We see this need from April 2024, whenever the date is, for 6 years or 10 years. We're going to enter into these long duration 10-year contracts. What are the solutions that you can bring forward in order to meet that system need? So that allows, therefore, the industry to look at what the needs are, to think about, well, how do they meet that need? Do they use traditional sources of sort of synchronous compensators and flywheels, or do they look to invest in the new technologies using batteries, grid forming inverters, and other sort of technologies that may not be even known to us yet? Obviously, in doing this, our primary aim is to seek the lowest cost solution to the consumer that delivers the best outcome. So really, again, looking at those needs and doing an assessment of what the market brings forward, both on a locational basis to see how effective it is, but also from a technology performance basis as well to see whether it does actually solve the need. So we go to market, we compete these things. It's a very much a tender process, looking at the value over 10 years. But to ensure that we still allow the transmission owners, the incumbent monopolies with regulated assets, to say, well, what would be the counterfactual, and actually would the transmission owners be cheaper for this particular solution in this particular area, then the transmission owners are allowed to submit a counterfactual into the process. So we get the full regulatory sort of price controlled solution and what that would cost the consumer over a 10-year period. And we can compare that with a fully commercial solution that's delivered by market participants. At the moment, these markets are still nascent. There isn't the liquidity or the volume of these services in the market to run a day ahead or a week ahead or a month ahead process. So as I said a moment ago, we very much worked with the industry and said, well, look, what would give you the right level of certainty to make the investment? And the first Stability Pathfinder contracts were for 6 years. And the feedback was, well, that's a good period of time, but it's not quite long enough. So our more recent Pathfinder projects have been looking at 10-year commitments. And we'll talk later about what have we seen coming forward and what sort of prices are we getting over that time period. So that's what Pathfinders are. As I say, we really need to move from calling them Pathfinders into something which isn't finding the path anymore. It's, as I say, sort of becoming business as usual. So what have we done so far? So phase 1, Stability Pathfinder phase 1, we were really working on what we now call phase 2, but actually we saw an opportunity in the market to go very rapidly and get phase 1 underway, which is to bring in inertia and dynamic voltage control very quickly. And what we wanted those products to be online by was by April 2021, so a year ago, we wanted these products to be live, so a very, very short period. So we expected existing assets would come to the market, which have tweaked how they operate to provide inertia and voltage control. So we weren't paying existing generators that were going to be on anyway and providing these services for free. This is where generators had to behave differently, operate differently, or invest in their kit in order to provide these services. So in phase one, for example, we got a CCGT, an old CCGT that was about to be demolished and decommissioned, actually repurposing itself and providing the inertia without the gas turbine. So it runs in synchronous with the system. We get the rotating mass and the voltage control from that. And it's provided jobs and security. And obviously, because the asset had already been written off, actually, that's a very low cost solution to bringing that forward. Also in phase one, we've had pumped hydro plants just spinning in air or in water, again at 0 megawatts and operating in a different way, which again, we funded for, but pretty low cost. But we also had other products that were coming to market, which were going to come to market for other reasons, and actually jumped onto the back of this. So GE has developed a rotating stabilizer piece of kit, and we procured 2 of those up in Scotland through phase one as well, and they just commissioned at Christmas of this year. And that phase one, that's about to sense of scale here, that's about £128 million over a 6-year period. So relatively low cost for, because there's still a couple more to connect to the system for 7 or 8 devices. Phase two, though, which is the one we've been really excited about. Phase two was for short circuit infeed in Scotland. Phase two coincided sort of just after we'd put grid forming inverters into our grid code here in Great Britain, which I believe is the first in the world. It's back to Mark's chicken and egg process. I believe in GB we've broken the chicken and egg cycle in that we now have a minimum viable product for a grid forming inverter on the system. But that did mean that in phase two, when we went to the market, we've procured 10 devices through phase two, 5 of which are traditional synchronous condensers, flywheels, etc. But 5 are batteries with grid forming inverters. So again, really using that new technology to think differently as to how we operate the system, but providing that short circuit infeed through grid forming. And then phase three, which is where we're just in the tender process now, looking across GB, again, focusing on short circuit infeed and voltage control, but we expect that contract award to be later in the autumn or in the fall, just after summer. So sense of scale of these things, stability phase two, that was about £330 million over a 10-year period. So £30 million a year for 10 machines, or 10 devices, I should say, which are providing short circuit infeed. So that's providing us system security and making sure the system is stable. It's allowing us greater integration of renewables and inverter-based resources. But more importantly, it's avoiding us having to run gas-fired power stations within Scotland to maintain grid system stability. So that £30 million a year is saving the consumers tens of millions of pounds a year, if not hundreds. And we expect certainly phase three, the benefits, because now this is really tackling exactly what the gas power plants are delivering to us in terms of short circuit and voltage control in those regions. We expect the value from phase three to be even greater. On the voltage side, we tendered for a voltage service in the Merseyside region, so the northwest of Britain, you can see on the map just there. And again, we went out and we said, what could you bring forward? And actually, in this case, the market brought forward a traditional reactor, just a shunt reactor, just like any other utility would have built anywhere around the world. However, because it was a commercially procured event, that reactor was probably less than 50% of cost of what a traditional TO would have delivered the same reactor at the same site. So again, it's just that different way of financing, that different risk profile that actually allows the commercial entities to deliver what historically would be called a transmission owner asset at much, much lower cost. However, in the Pennines voltage Pathfinder, which is the next on the list, this was much bigger. It's covering the orange blob on the map. And actually, the transmission owners came in at 50% of what the commercial providers could provide. So you can just see how this commercial tension, allowing the transmission owners to compete, and well, not compete, but to provide a counterfactual to the commercial solution, can also provide value. but it flips and it flops between the different locations, the different challenges of those locations, and the strategies that the bidding commercial entities play, and also the regulatory deals that the transmission owners have. So it's absolutely crucial, I think, that any sort of commercial solution in this type of space where the services could be provided by a traditional utility, that they should also be able to participate in some way, so you can be sure that you're getting the best value for the consumer. And then finally, constraint management, so huge power flows crossing that blue bar from Scotland into England and Wales, a lot of wind in Scotland, not a lot of demand. Looking to find ways very quickly in which we can help to manage that before some large infrastructure comes into play in the next 4 or 5 years. And intertrip, so putting generation on intertrip is one of those. So we ran, again, a commercial tender process. We got some there were some sites already connected to an existing intertrip, but it wasn't commercially viable. We've made that commercially viable, and those machines are now, or those generation sites are now participating and playing in this intertrip scheme. And for the 2 weeks it was armed, at the beginning of April, we saved £6 million, or 77,000 tons of CO2 by arming these generators to intertrip. And as we get to October of next year, October 2023, that intertrip scheme will be expanded to include many, many more generators. So again, we can add more and more capacity to that boundary, reduce costs to the consumer by reducing the constraints, and obviously reduce the carbon emissions because we're not having to procure the gas to replace the wind that we have constrained off. So lots of activities going on in this space. And there's more to be done. So as we look to the future, the phase 3, as I say, we've learned all the time. So these are more detailed as to those regions where we're focusing on. Can everybody still hear me?
Julian, can you hear me?
Yeah. Yes, I can.
We just had a complete and absolute blackout of the internet for about a minute. So
right.
Could you? Yeah, and that was me ringing you. Sorry about that. We've no idea why. So could you go back about a minute?
Maybe. I mean, on this slide, where did you get up to? Did I talk about Pennines?
Did you talk about
Pennines?
Oh no, you'd finished constraint management.
Okay.
I think you'd finished this slide. I think you were just about. Yeah, you were. So this slide. Okay.
This one. Okay.
Sorry about that.
So again, that's okay. So these are Pathfinders, as I said. So what have we learned? So phase 3, rather than it being a free-for-all trying to get access to the grid system, actually we are now reserving bays with the TOs, transmission owners, before we go live with the market. So actually the market knows there's a bay that's available. They know when it's going to be available and how much it costs. And then they can focus in on their bidding strategies for that particular location, rather than the scattergun approach that we've had in the previous Pathfinders. We allow participants to come with us to look at site visits and get a sense as to what are those physical challenges going to be, which again allows and facilitates earlier access and better quality bids into the process. And also previously we had a technical submission. If you passed technical, you then went into commercial. We've now combined those things together. So when you submit into phase 3, you're submitting your technical solution and the commercial arrangements that go with it, which takes 6 months or so out of the entire end-to-end process. So it's a much more streamlined process. The market and the industry and GB is getting used to these things, and we are getting more and more innovative solutions coming forward, which is benefiting the consumer and driving down costs. So as we look to the future, this is just the foundation. The Pathfinders I've spoke about so far just get us to 2025. So this ability for us to operate the GB system at 0 carbon just for a few hours in 2025. We then need to move very quickly after that to extend those few hours into a few days, few weeks, few months, and then by 2035 to be 100% of the time. So we've got more of these Pathfinders, or whatever they're going to be called, procurement processes going forward to buy more and more of these devices. And we hope at some point that there'll be so much certainty in the market, we'll be able to forecast where the price is going and the need is going, that actually we won't need to enter into 10-year contracts, because people will just be building these devices and bidding them into a liquid market, as they would do for frequency response and others. And actually we can stop these long duration procurement processes, and it just becomes a regular market, just like, as I say, frequency response services are today. So that's sort of where we are. That's what Pathfinders are. So that's how in GB we're incentivizing the market to bring forward solutions, but to innovate in doing that, to drive down costs for the consumer and ensure that the devices they're bringing forward are meeting the needs of the system operator. And that's what we are putting out there into the market. So with that, Mark, that was all I was going to say.
Can you hear me? Okay, thanks, Julian. Very good. And just for everyone's information, that Julian is right. I mean, the UK has broken the chicken and egg situation, and I think they're probably the leading system operator in this area in the world, in my opinion. That's not me just being a political or diplomatic Irishman. It's just me being talking the truth. Okay, so we'll have questions after this. So Tony, you're up next, and like I said, I think everyone needs to give Tony a round of applause. It's now 3:30 in the morning.
All right, thanks everyone. I hope you can hear me.
Yeah, let me introduce you though, Tony. So Tony Morton
Yes.
is the global technical head of power systems of, I don't know how to pronounce it, Vyus Group, but they used to be eConnect, if anyone remembers them. It's an easier thing to remember. He's also an adjunct professor at Monash University in Melbourne. Okay, Tony, over to you.
Thank you, and I hope you can see the see the slides. The screen sharing is working, so that's great. And fingers crossed we don't have a network outage. But yeah, so what I'm talking about here is some of the work we've been doing on behalf of the Government Renewable Energy Agency in Australia, particularly looking at the trying to get some quantitative ideas around the suitability of grid forming batteries to contribute to system strength in the Australian market. So a little bit of context, first of all, and here we go. So we were engaged by ARENA, it's called, the Australian Renewable Energy Agency, to investigate the role of grid forming batteries to improve system strength and enable greater penetration of IBRs. We've done that in a number of stages. The first stage was really a bit of an exercise in comparative assessment using a fairly simple technical methodology, which I'll talk about in a minute, to see how differences in location and sizing and concentration of these plants can affect their certain metrics for grid strength. And we're supplementing that now with more detailed technical investigations, looking at the dynamic behaviour of fairly generic grid forming converters and how that compares with other system strength remediation options. We're also at the same time helping to provide a bit of an independent assessment of various OEMs' technology in collaboration with those OEMs to just to really provide an additional level of assurance that that these system strength contributions are real. So that involves doing some modelling, also reviewing documentation. I should stress that it's not feeding directly into ARENA's decision making on the funding for various projects, but it's just really to add a layer of independent technical assurance independently of their decision making process. So I'm sure they'd want me to make that very clear. So a little bit of market context here. In Australia, we have our National Electricity Market, the NEM as we call it, and it's moving to an approach to system strength where instead of relying on individual connection applicants with IBRs and other technologies to each to remediate their own system strength gaps or where there is a risk. We're moving to an approach where there's actually an option to provide this system strength remediation on a utility-wide basis, and for connection applicants to essentially pay the operator to participate in that centralised procurement. And in that way, it's hoped that the remediation of system strength network-wide can become more efficient and more cost effective, and there's additional flexibility in how that remediation is provided on a whole of system basis. So the key elements of this process, which is still in the process of being designed, I should stress, is first of all that there will be an annual assessment by our market operator, AMO, of the system requirements for system strength. At the moment, that's couched in terms of fault levels, obviously, and that's a measure that I again will talk about in a minute. Where we look at an individual IBR connection, we do identify a gap between the minimum and the available fault level, if you like, or other suitable metric of system strength. They'll now have the option. They can either self-remediate as they do at present, or they can pay for a suitable share of centrally procured system strength services. And then the provision of those system strength services is procured by the network operator, but third parties are able to bid into that process. And the idea is there'll be a competitive market in system strength services ultimately, which will then facilitate additional IBR connections. So underlying this whole process and the incentives that are going to come out of this process to participate in a market for system strength services and to guide decisions about self-remediation or central remediation, there's a whole lot of technical work to be done. And the idea is I'm looking here to just provide a taste of that. So the first thing that needs to be determined is some criteria for determining this concept of stability of the voltage waveform, which is what's supposed to underline system strength. And this is something that AMO is working on in consultation with the industry. There's also the whole question of locational factors. So clearly, if you're providing a network-wide system strength service at one node A, and you've got an IBR connecting at another node B, then the extent to which that system strength remediation assists with the connection of that particular IBR and enables it to contribute to the stable operation of the system is going to depend a lot on where A and B are. And very crudely, you can imagine having a measure of electrical distance between the two, which will tell you to what extent you may have to discount the contribution from that service at node A when you're looking at that particular connection. Getting a proper handle on reliable locational factors of that sort is going to be critical to the market operation and the incentives that are provided. So clearly there's a lot of technical factors underlying this. So if you'll indulge me, I might just spend a few minutes talking about how we try and get an idea of a quantitative idea of system strength contribution and the readiness of various remediation measures, including grid forming plants, to contribute to that. So if I can go back to first principles, I guess, if we look at the traditional picture of power system operation, it's essentially regarding the power system as a large machine, and it's an electromechanical perspective. If you like, it's the analog perspective of power system operation. So that's the one we've traditionally had right through the 20th century. So it's one where we have power flows in the network that are actually regulated by physical rotating masses attached to the rotors of synchronous machines. And those rotor positions translate into phase angle differences between the network voltages. And electrically, when you look at the power flow solution for the network, those voltage phase angles are what essentially determine your relative power flows among the various nodes in the network. So the voltage phase angles, they're tied to the synchronous rotors, and they also regulate the power flows. And in this way, we get synchronized stable operation with power flows determined by relative rotor positions of the generators. And then on top of that, we have excitation systems that are regulating the voltage magnitudes, which are to a certain extent decoupled from what's happening with those power flows. And then when you have a fault in the network, of course, we see a fault current contribution from each of those machines, which is essentially determined by Ohm's law. We basically look at the EMF of each machine, we look at the impedances of the network, and we do a very basic network calculation, essentially Ohm's law, that tells you how much fault current you get at any particular location. And the fault current that you get there is in fact a proxy for the electrical distance of that fault point to each of the generators. And that is what has made short circuit levels, fault levels, short circuit ratios, whatever you call it, a useful measure of system strength, because it acts as a proxy for that electrical distance. So when we move to a network based on a system based on IBRs, we now have a bit of a different picture of power system operation. It's the digital perspective, if you like. So what we're looking at now is potentially operating a power system not as a machine, but as an electronic appliance. And what we have now is power flows regulated not by physical rotating masses, but by the modulation angles of synthetic voltage sources inside power electronic inverters. Now, they can be programmed in different ways to provide different voltage source characteristics. And of course, the foremost among those at the moment is looking at getting them to operate as a virtual synchronous machine, so that we have a virtual equation of motion that's determining the modulation angle or the phase angle of the EMF that inverter now is presenting to the network. And then, similar to machines, we have outer loop controls that are maintaining voltage magnitudes. Again, very similar to what we do with synchronous machines, except of course that there's no intermediating magnetic circuit. And then when we have faults in the network, we have a rather different picture of how the inverter contributes to the fault. It's no longer purely a passive contribution determined by Ohm's law, because quite often these inverters will go into a current limiting mode. And the fault contribution for these inverters often has to be explicitly controlled. So we, on the one hand, we have the flexibility to say the inverter should make a contribution according to the depth of the voltage dip, according to some rule which can then get programmed into the firmware. But on the other hand, we don't have that automatic proxy for electrical distance that determines what your fault current is going to be and allows you to coordinate your protection. So we've actually got a very different picture now of what the fault currents in the network look like. And it also means that we can't necessarily rely on those fault currents as directly as a measure of system strength, because they're not reflecting the passive characteristics of the network anymore. So I guess we can then look at system strength itself using two viewpoints. So just looking at this for a typical branch in a network, we've got two voltages at each end of the branch, and we've got a certain branch impedance. And we can look at how the power flow on that branch relates to characteristics of those endpoint voltages. And this gives us different measures of the stiffness of the network relative to the change in voltage that you get for a certain change in power flow. So on the left, we have a basic formula that determines the power flow as a function of voltage magnitudes, or if you like, the magnitude stiffness of the network. And So on the left-hand side of that, we have essentially the reactive power Q with a correction that depends on how much resistance there is. If we've got a lossless network, then it is just Q. And that relates directly on the right-hand side to the difference in voltage magnitudes between the two endpoints, scaled by this quantity V1 on X. On the right-hand side, we've got another formula that talks about angle stiffness. And on the left-hand side of that formula, we have the active power flow P with a correction that again depends on the network resistance. And then on the right-hand side, that power flow P relates directly to the difference in phase angles between the endpoint voltages. And again, it's scaled by a V1 on X quantity. So both of these are determining at a very fundamental level and at a quantitative level how differences in magnitudes and angles of voltages relate directly to differences in the active and reactive power flows. And of course, when you look at the when you look in particular on the right hand side at the behaviour of phase angles, what you see is that as power flows change, we get a change in the separation of those phase angles, and if that's allowed to continue, then that can actually translate to movements in the system frequency as well, because the frequency is just the rate of change of those phase angles as we see them evolve in time. So there at a fundamental level, before you even talk about machines, we're talking about a relationship between active power flows in the network and perturbations in the system frequency. And then this quantity V1 on X that appears in both of these formulae as a scaling factor, well, of course, this is simply, if we imagine that we have a low resistance and we just set V2 equal to 0, and we look at the current flowing, V1 on X is just the short circuit current that obtains if we put a short circuit at one end of this branch and look at the current delivered from the other end. So that's what underlies the use of short circuit currents and short circuit ratios as proxy indicators for strength, because it feeds directly into the proportionality constants in the stiffness formulae. So what that has led us to do when we're trying to get quantitative metrics of system strength that don't depend on having fault currents that are determined by passive Ohm's law characteristics of the networks, we can take a different approach. We can actually look directly at the sensitivity of voltage magnitudes and angles in the network to small perturbations in P and Q injection at particular points in the network. So you can imagine that we have a kind of Jacobian matrix here. And so this is just talking about the relative change in voltage magnitudes and voltage angles equivalent to a certain change in P and Q injection at a certain point in the network. And the way that we look at this is we determine the sensitivities not from the conventional load flow solution where we have fixed P and Q and fixed voltage magnitudes, but we actually go right down to the basic circuit equations, the YV equals I equations from the system admittance matrix, and determine the sensitivities that way. And we can actually use power system analysis software to drill down directly into that picture and get those sensitivities from a basic modified type of power flow. And when we do that, there are essentially 4 coefficients, because we can look at the sensitivity of magnitude and angle, and we can look at the sensitivity to changes in active power or reactive power. And the 2 key ones there is the one we call AP, which is the sensitivity of angles to active power, and MQ, which is the sensitivity of magnitudes to reactive power. And when we abstract to the very simple case of a network modeled by a single equivalent impedance, and we assume that impedance doesn't have too much resistance in it, we can relate those sensitivity coefficients directly to the traditional fault level that we get from a short circuit analysis. But the advantage here is that when we do these sensitivity calculations, we're not actually applying short circuits in the network and measuring fault currents. We're actually just doing incremental power flows and looking at sensitivity coefficients, but we're getting the same numbers out of this. And that's really the key here. So that allows us to talk about quantitative metrics of system strength that don't depend on the precise behaviour of fault current from different kinds of technology. So there's still basically steady state based metrics. So we're not looking into any detail here on the dynamics of the network or stability studies or anything. These are just very simple numbers that we pull out of the power flow characteristics of the network with specific kinds of generation connected to it. But we can use this to get metrics of system strength across the system that aren't sensitive to the particular generation technology we're using. So just as an illustration of this, we've done this exercise using a very simplified picture of the Australian NEM, the power system. So this is a 68 bus test network that's just abstracted from a very broad brush picture of the Australian system. So these are just labels for different Australian states and the interconnections between them. And we can actually then do this basic power flow analysis and get a kind of heat map of these sensitivity coefficients. So this is the angle active power sensitivity. So one of those 4 sensitivity coefficients that we can derive from doing some basic incremental power flows. And we see that it does pick out the particularly strong and weak areas of the network. We see in particular, there's one particular area of the Australian system called West Murray that's known to be particularly weak. And we see that reflected when we do the sensitivity calculation. But this by itself isn't enough. This does give us some very useful metrics, just like short circuit levels and short circuit ratios do. But it's also important that we back that up by understanding the actual dynamic stability behaviour of these different technologies. And so just showing a typical case study, we've taken one of the large generators in the Australian system, and we've pulled that out and we've replaced it with an 800 megawatt grid forming BESS using a fairly generic model to study the dynamics of that, just to see how it affects the stability behaviour of the system overall. And in general, we can look at dialing down the synchronous generation in this network, replacing that with certain mixes of grid forming batteries with grid following IBRs, and seeing how that affects the stability. And so we can do studies in PSSE or PSCAD software and see what happens. This is just a comparison of the active power response to a fault. When we have, on the one hand, the black trace is with the existing synchronous machine in place, and the blue trace is when we replace that with a fairly generic virtual synchronous machine, a grid forming inverter. You'll see there's quite a bit of oscillation here, and we can understand this because the generic grid forming converter we're using in this case doesn't actually have a power system stabilizer in it, whereas the synchronous machine has. And what this points to is that the grid forming inverter is doing the job in giving us the stable power flow, but it's a bit wobbly because we've actually done away with the traditional thing that we know synchronous machines need to have, which is stabilizers to provide damping in the power system. And this does point to the desirability of having that same damping contribution put into the control system for the grid forming converter. And there are a number of ways we can look at doing that. That's something we're looking at the moment. We can also see, though, that if we look at voltage phase angles in the network and the displacement in those on recovery from the fault, we can see how these angles move around in the original system with a synchronous machine, and we can likewise see how they move around when we replace that with a grid forming inverter. And by and large, we see fairly similar stability characteristics as long as we have the control system tuned appropriately. So we can actually replicate the stabilising behaviour of the machine with things like virtual stabilising torque and so on with the power electronic plant. And we can also look at the reactive current response to the fault. And again, we can see that even though our generic grid forming inverter does have a current limiting behaviour, so the fault current doesn't peak at the same instantaneous level that we see for the synchronous machine. Nonetheless, it's a very similar fault current behaviour that we see, subject to that limiting. And the stabilisation of the system, it seems, does not critically depend on the peak magnitude of this fault current. So even though we don't get, and we don't expect to get, the same level of maximum fault current contribution from power electronics that we get from passive synchronous machines, nonetheless, we can still expect them to make a similar contribution to the stabilising behaviour of the system. So this is a slightly busy slide, and this was really just intending to sum up some of the preliminary findings we've made on the various locational factors we've found and the sizing factors with grid forming plants in the Australian network, and how the contribution they make to system strength on these basic metrics depends on things like location and size. So obviously we do have a size effect. That's the first dot point. But the second dot point says that we do see a non-linearity in that contribution. If we look at the strength contribution of a 200 megawatt grid forming plant compared to an 800 megawatt plant, the 800 megawatt plant doesn't actually give us quite 4 times the strength contribution. So there's a little bit of a law of diminishing returns, that the first 200 megawatts you put in has the biggest contribution. The next 200 megawatts has a slightly smaller contribution. It still makes a big contribution, but we see that contribution get just a little bit less as we increase the size at the one location. And related to that is the third point here, that if we're able to take a given amount of inverter capacity and split that up and spread it around the system at smaller points, again, intuition tells us that we should be able to get a good system-wide contribution from that dispersal of plants. And in fact, we do see that again when we look at the quantitative metrics from our power flow studies. That there is a benefit from spreading these out versus concentrating the same overall capacity just at one point in the network. We see a bit of a location effect as well, depending where we put those dispersed grid forming plants. When we put them in the parts of the network with the highest load, generally speaking, or if we put them in urban areas, we actually do get a slightly greater effect than if we put them in areas where there's not a lot going on in that particular part of the network. So considerations of location do make a bit of a difference. It's probably a secondary effect. We still get the system strength contribution no matter where we put it. But if we're looking at the most bang for buck in terms of the overall effect on customers, then we see that putting the grid forming plant where the customers are is actually getting us the greatest effect. We also did a very quick comparison with fairly generic synchronous condensers, and we do see a similar contribution, although the synchronous condensers were still making a greater contribution in our studies because we actually assumed that. So we took a conservative approach, and we deliberately wanted to kind of bias things in favour of the synchronous condensers, just so we weren't drawing too optimistic conclusions for grid forming plants that are still an evolving technology. But what we do see is that they're still making a very impressive contribution to system strength compared with synchronous condensers, even where those synchronous condensers are optimized to the extent that we know we can do them now based on 100 years of experience. And we don't make those same assumptions about optimizing the grid forming converters. We still see we still see that contribution being made.
Tony, can you wrap? I know you're nearly at the end, but can you just wrap it up? Yeah, good man. Thanks.
Absolutely.
Yeah.
So just a few observations there, and then this is my last slide. So just talking about some of the ongoing work we're doing with ARENA. As I say, there's lots of work to be done here in developing this technology and actually making sure that it contributes to the market properly and optimizes that. So one thing here is we do want to see PSS type feedbacks being incorporated into these control systems. Fortunately, we know all about the theory of oscillation damping for synchronous machines, and most of that will carry over to the to virtual machines in grid forming converters. We look at different current limiting strategies. It's not necessarily the case that you get the best response to faults from grid forming plants just by prioritising reactive current, the way that we've been doing with our grid codes at the moment. It may be better just to freeze the modulation angle and then resynchronize when the fault is cleared. And comparing RMS and EMT model performance is a very important aspect of this as well. But I'll leave it there and hand back to you. Thank you.
Hey, Tony. Thanks, Tony. That was very good. So I think there's some very interesting questions actually arising from the comparison between what you're saying and the sort of you're using Ohm's law, which is good, and some of the comments that Julian made. In the interest of just to cover what John would have said, I'm not going to say exactly what he would have said, but I'm going to just show a few quick slides, just to make one or two high level points about DS3 very, very quickly. Do you want to put them up there, Ryan? So John sends his apologies, but do you want to just put them up there? So I'll take 2 minutes. So just very quickly, the history of DS3 is that there was an all-island grid study done in Ireland in 2008 about renewables, and I was involved in that. And a facilitation renewable study was done in 2011, and DS3 was introduced to address the issues raised. Essentially, what happened was studies were done, and they said, there's certain technical issues raised. I just point out that this is more than 10 years ago. It's before grid forming. I mean, did grid forming exist then, Deepak? Did grid forming exist 10 years ago?
Sure, why not?
Yeah.
We just didn't know it as grid forming.
Okay, that's fine. Okay, so it introduced the DS3 program. Next slide, please, Ryan, very quick. Basically, I think many of you know me, have seen this graph before, right, many times. This is essentially what came out of all those studies in essence, was that the Irish system could operate to 50% SNSP. This is essentially a ratio of, it's a penetration level ratio if you want. But beyond that, they had problems. Okay, and the DS3 program was introduced to go from 50% to 75% to keep the system secure. So for the past 10 years, and I think it's very important to point out, this was based on work that goes back nearly 20 years. Next slide. So the DS3 program, so just to show you, this is the 10th of May, 2020 in Ireland. And as you can see, I know that, wow, yeah, you can't see the demand, can you? Yeah, that's the problem with PowerPoint. There is a demand curve in there somewhere. I think, what do you mean? Orange is, yeah, orange is, the actual wind generation is there somewhere. You can't, it's not showing, sorry. But if it showed it, it would be tracking it. And the reason is because they had this limit. So the reason the wind seems to track the load in Ireland is not because it actually tracks it, it's because this ratio has to be kept, and therefore control actions are keeping it. Next slide. And that's just showing you March, April 2020. Show you again. I'm sorry, it doesn't show it, but it shows you there's a lot of wind in Ireland. I think it was 46% of all the load was supplied in March in that period for 1 month in the whole system. Next slide. So the summary is that they set up the DS3 program, and what they did was they introduced new services, which is what we're talking about today. And you can see them there. I'm not going to go into detail because that's for EirGrid to do, not for me to do. I know a little bit about it. I was involved at the start, but I haven't been keeping an eye on it. But in March 2022, they hit 75% SNSP. So now operationally, EirGrid can go to 75% SNP. So it shows you that, 10 years of work defining new services, and then defining new services, implementing grid codes, performance monitoring, and incentives. So when we're talking about incentives, I think it's just carrot and stick here. Yeah, they have to make sure that they perform. So there was a bit of money, there was a bit of carrot, there was a bit of stick, etc. Really important thing is that they're now planning on going to 90% SNSP. So that's it. Thanks, Brian. Close that down. I just wanted to give a sort of a little, rough picture for EirGrid.